So, ladies and gentlemen, yesterday I had asked you to just try the homework, and I don't know how you did, but let's get that out and see how you did. And I have to find that page. I don't have my normal book today. So this is the one that the first question started out about the color of rental cars available on the lot. Is that correct?
Yeah.
Okay. Now, guys and girls, I'm going to tell you, the whole thing about stats is it's new. You're going to see this type of stuff a little more often. You'll see this stuff pretty much all through high school, no matter what math class you're in. And then obviously if you take statistics, you'll see it there. And statistics will goof you up a little bit. There's little tricks of the trade that work. Working. Please work. Why we're not working? What's going on with the? There.
They have to calibrate it or whatever.
I just did.
Have to do it again.
No, it's not even reading it for some reason.
What is it, mister? You gotta click it like top, middle, bottom.
Yeah, I already did that. I don't know what's going on. Let's see. We are definitely off. All right. Let's move this a smidge. And recalibrate. Yes. Yeah. Do. Why not? That was the notes from yesterday and the sheet roll. All right. Let's see if this works now. Maybe. No. Plugged in. Go for it. So I'm just going to walk through this homework. Please mark up, do any notes that you need to do on this, and that's fine. So as below are the colors of rental cars available on a particular car lot. They have black. There's 12 of them. Silver, we have 8 of them. White, we have 8 of them. Red, we have 3 of them. And blue, we have 4 of them. Okay? So when you're dealing with statistics, it's important to see how much your foundation is. Okay. Pass that back to Danny. So how many cars are we talking about? Let's see. 12 plus 8 is 20.
35.
Oh, it's 35?
Yeah.
Is that what it comes to?
Yeah.
Thank you. So we have 35 total cars on this particular lot. So question A says, what's the probability that the next car off the lot is white, assuming that we're person's not selecting, like they're all lined up. So how many white cars are there? 8. So we have 8 out of 35. Okay, so the probability of a white car is 8 out of 35. You can keep it as a fraction, you can turn it into a decimal, or you can turn it into a percent. They're all correct. Okay, I'm just going to leave it as a fraction for sake of time. If you don't know how to convert a fraction to a decimal, come see me. What is the probability the next car off the lot is black? Is it black or what? Silver? Or silver. Okay, so we have to add up how many black and how many silver cars there are. How many? Yeah, 20 over 35. And the one thing in statistics, you can leave it like this. It's sometimes, depending upon your teacher, how and I'm happy with it. Just leave it like that, but you can reduce it. So 5 goes in both. That's 4 over 7. So you have a probability of 4/7 to that those two types of cars go off the lot. What is the probability that the next car off the lot is black or blue? Okay, probability of black or, and we'll have to call that one blue or blue. So you add up, you have black cars, you have blue cars. It looks like there's 16 out of 35, and I don't think you can reduce that. And then what is the probability that coming off the lot is red or black? So probability of red or black. Okay, so red is 3, black is 12, so I have 15 out of 35. That can reduce. 5 goes in both. So you get 3 over 7. And then what is the probability the next car off the lot is not red? Right, so what you should look at is the probability of red is 3 out of 35. So that means that there are 32 other cars on the lot. So the probability that it is not red is the complement of that, which means it's 1 minus 3 over 35, which means that's 35 over 35 minus 3 over 35, which means, extend you, that's going to be, I'm just doing the arithmetic to show you, but I think most of you can see in your heads that it's 32 out of 35, is that right? Okay, so again, the complement is a valuable tool because sometimes it'll allow the problem to become a little bit easier if you choose to use the complement. Okay? Does everyone feel okay with problem number 1?
Yeah.
Problem number 2, we're talking about a jar of marbles. Come on now. Jar of marbles. So you have some jar and there's some marbles in there. Okay? I'm not going to draw all 100 out. I'm sorry if you were looking for that. We happen to know there's 25 red, and we have 25 blue, some blue, and then 25 green, and 25 black marbles. So they tell us there's 100 marbles. So that'll become our denominator. Find the probability if the marble is drawn at random that is red. So the probability of red is 25 out of 100, which reduces to 1 out of 4. Okay, 25%. So if you just draw one marble at a time, 25% of the time, you should draw a red. Does that mean that if you pick a red and you put it back in, shake it back up, that you're going to pick a different one? You can still pick a red. Okay. Find the probability if you pick a marble at random, it is blue or black. So blue or black. Okay, so the blue and the black, that's 25 and 25, that's 50 out of 100, which we can all reduce that. We have a 1 in 2 probability of pulling. Okay, find the probability if the marble is drawn at random is not green. So let's find the probability of green first. The probability of green is going to be this, which reduces to 1/4. So the probability of not green is doing the complement of that, 1 minus 1/4. And I'm showing you the correct way to go through it. Yes, you could do it in your head simply because we're showing you a lesser version of it. So that comes out to 3/4. Okay? Again, the complement is a valuable tool to utilize. Okay, letter D. If I pick one marble, look at it, replace it, and then pick another marble, what is the probability that they are both red? Okay, so you're picking twice now. Picking a red and a red. And it has replacement. Okay? So that means our denominator is going to stay the same. So I pick a red, that's 25 out of 100, which is 1/4. That marble that goes back in there, and it's all shaken up, it doesn't remember being picked. So the probability of picking another red is going to be 1 out of 4 again. So you multiply those together, and you find that you have a 1 in 16 probability of picking a red, shaking it back up, and then doing it again. Does that make sense how I just said that?
Yes, sir.
Yeah.
The green one.
Yeah.
You said it's not red.
Oh, so this would have been 75 out of 100 originally.
Yeah.
Because I know that probability of green was 1/4, which is 25 out of. You're absolutely right. I just had reduced it first. So if you left it as 75 over 100, you're perfect as well. I was just reducing the fraction. Okay. Question? No, good. Okay. All right. Let's see. Let's move down a little bit. Where am I at? That's not green. Did we just do not green? No. Oh, we're at E, right? E. Thank you. Holy cow, that's a long problem. If I pick one marble, look at it, replace it, then pick another marble, what is the probability that neither are blue? Okay. Okay, so you're picking 2 picks, and you're looking for not blue and not blue. Okay? So we can do this one of 2 ways. We can do, let's find the probability that it's blue and blue and then take the complement of that. Or I can say that I know that not blue is 75 out of 100 and not blue is 75 out of 100. Okay, probability of not blue. Let's reduce these. It'll be more friendly. So I have 3 out of 4 and 3 out of 4. If I multiply those together, I find that 9 out of 16 times. If I were to pick and then pick again, where I put in the middle, then I get a not blue. I get not blue and not blue. Any questions about these so far? And this is the basic foundation of how gaming takes place, whether it's a game that you play at home or a game that you know, if you went to a casino later in life. This is the foundation of where they start. They start realizing, okay, these are the probabilities, and they start figuring out what the outcomes are to do stuff. So, am I on letter F now? Okay.
Was that K?
That was E. Okay, letter F. If I pick one marble, look at it, replace it, then pick another, what is the probability I get at least one green? Okay, so I have a pick and a pick. I replaced each time, but I want to know I get at least one green. Ooh. Okay. So I think what we can do is we can work with the complements on this one. I think it'll work out a little bit easier. Because does at least one green mean that I could have a green and another color? Or I could have a green and a green? Those both mean the same thing? Agreed? And if I get a green marble, I don't know if it's the first or the second marble. If I obviously get 2 greens, obviously they're both. So if you go the longer way on this, it's going to take a lot longer to figure out. So let's do this. Let's find the probability of not green and multiply it times the probability of not green again. So we're doing the complement. Does that make sense how I said that? So there's 25 green marbles. There's 100 total marbles. So how many marbles are not? There's 75. And if I reduce 75 over 100, what do I get? 3/4. Does everyone agree with that? So not green means 75 over 100, which reduces to 3 over 4. Does everyone feel comfortable with that? So this is also 3 over 4 over here. Now, what am I looking for in this problem? What did it ask for? At least one of them's green, right?
Yeah.
But they both could be green as well. Okay, so this is kind of goofy that we are taking this problem here, and we're looking for. Yeah, you know what? This is going old school on me. Yeah. I think this might be the original smartboard, which isn't that old, but I don't know how long it will last. All right, so what is the probability I get at least one green? So I'm choosing to do the complement and do the math that way. So if I multiply 3/4 and 3/4 together, are you kidding me? There we go. All right. Yellow. Really? That's the color we're going with today. Okay. Pen. Good. Yes. Okay, I'm just going to choose a black pen. We're not changing colors today. Okay, so if I multiply 3/4 and 3/4 together, I get 3 times 3, which is 9, 4 times 4, which is 16. Okay? So that's the probability that neither of them were green. Does that make sense how I said that? Make sense? But we want to know what the probability at least one of them was green. So what I'm going to do is I'm going to do the complement of that. So I'm going to go 1 minus 9 over 16. Well, I changed that to 16 over 16 because that's the same thing as 1, right? 16 minus 9 is 7. So the probability that I pick my marble, put it back, and I pick another one, that I have a green and another color, or another color and a green, or a green and a green, is 7 out of 16 times. Okay? That's a curveball a little bit. And if you think through it that way, I think you're going to find a lot more success. Okay? So, there, we're going to move on. Can I go, so where that was F, I'm going to G. We good? All right, letter G. If I pick 2 marbles without replacement, what does that mean if I didn't replace something? I didn't put it back. So how many marbles did I have on my first pick? How many marbles existed on my first pick? 100. 100. If I don't replace it and I pick another one, how many marbles are on my second? 99, right? Okay, so this is not replacing. So my first pick is going to be out of 100. My second pick is going to be out of 99 because I'm not replacing it. Does that vocabulary make sense? When we replaced it, we kept the 100 marbles. Okay, so letter G says, if I pick 2 marbles without replacement, what is the probability I get both red? Oh, both red. So the only combination we're going to get is red and red. So, quick question. How many reds are in our jar? 25. Okay? Now, we are assuming we picked a red. So if I picked a red, how many reds are left in the jar? 24. Does that make sense? Okay, and I need your help on this one because I can't do this math. I can do the bottom math pretty easily. That's 9,900. What is 25 times 24?
Oh, I got you.
Thank you.
25 times 24 is 600.
600. Okay. So I can reduce 600 over 99. I have 0, 0, 0, 0. So that becomes 6 out of 99. I can reduce 6 over 99 to 3 goes into both to 2 over 33. So the probability that you picked 2 marbles and you didn't put the first one back is 2 out of 33. That means that there are 31 other combinations that could take place on this. Okay? That's a pretty low outcome. Do you agree? You know, if you go and want to order a pizza and they'll say, hey, you have a 2 out of 33 chance that we're going to get your order right, you have a better chance of the order being wrong. Does that make sense? And I'm trying to turn it into terminology that you'd be like, oh, okay, I could understand what that's going to go with. All right, letter G, we're on H now. Oh my gosh, this is by far the longest problem I've ever seen.
That's the alphabet.
It is if I pick 2 marbles without replacement, so I have 100 on the first, 99 on the second, right? What is the probability I get both blue? Okay, well, I have 100 and I have 99. And both blue. Okay, so there's 25 blue and then 24 blue. So that actually comes out to the exact same thing because we had 25 marbles of each color, right? 25 and 25 and 25 and 25. So that's both blue. Okay? I picked 2 marbles without replacement. So again, I have 100 in the first one and the 99 in the second. What is the probability that the first one is blue and the second one is black? Okay? First one's blue, second one's black. Okay. All right, let's think about this. I'm on letter I. Everyone's okay that there's 100 here and there's 99 here? Is that okay? So I reach in, pull out a marble. What's the probability it happened to be blue? 25. Okay? So this is the blue. Okay? Now, assuming we picked a blue, that now means we have to do the black, but there's only 99 marbles in there. How many marbles are black though? 25, right?
Yeah, but you don't replace one.
Right. So that's why this one will be 99 here.
Yeah.
So then I have 25 again. So that's then 625 over 990. I believe I did that right. And just for those of you who like to see reduced fractions, let's dance this way. 625 divided by 990. Math fraction enter. Comes out to 25 out of 396 if you reduce that fraction. Again, I'm not too worried if you reduce it. Okay, both those answers are correct. So you have a pretty good chance that that wouldn't happen. Agree? Does everyone feel comfortable if I make that statement? There's a really good chance that I am not going to pick a blue and then a black in that order. Sound all right? Letter J. And please, but all means, you should be doing notes on here. That's totally fine. If I pick two marbles without replacement, okay, so we have 199 between our choices. What is the probability to get one blue and one black, either order? Ooh, either order. Either order. 100. So I get a blue and a black. Order doesn't matter. Blue or a black, order doesn't matter. So the question before was I got a black or I got a blue and then my next choice was a black. Now this one is I got a blue or a black, order doesn't really matter. Do you think it's a better chance that this can happen? Think about that. Jar of marbles. I pull a marble on letter I. I have to pull a blue, and then I have to pull a black. Right? This one says I can pull a blue or a black in either order. How many more outcomes are going to take place? How much? No. Think about this. Hang on. So I just did this. Here's my jar of marbles. I pull a marble out and I put it down, and then we have a slot that says, pick one, and then I pick another marble out and I put it into pick two. Okay? So there's only that one way that's going to take place, which was 25 out of 396. But now it doesn't matter. I'm just picking two marbles out, and it doesn't matter if I picked the black one first or the blue one, or the blue one first plus the black one. So how many more outcomes are going to take place in this case? Go with a real simple number. 2. That's it. You have twice as many more outcomes. So if I have twice as many outcomes, I just have to multiply the top by 2. So I have 50 out of 396, which then I can reduce that to 25 over. You said that originally? Oh, I'm so sorry. I gotta open my ears these days. Let's see. 2 goes in that 1, 9, 198. So 20. So you have a 25 out of 198 chance versus a 25 out of 396 chance. So if your friend says to you, hey, we're going to play a game, and you have this back, and they're like, hey, we're going to see the probability of picking a blue or a black, and you say, does the order matter? They're like, no. You have a better chance of that happening than it not. That's kind of weird. So we didn't even have to go through really the math. We just had to realize that right up here, order mattered up here on I, but on J it didn't matter. Okay. We are finally to the very last question on this particular problem. We are on K. If I pick 4 marbles now, still 100 in the jar originally, without replacement. So first pick, 100. Second pick, 99. Third pick is what then? Third pick's how many marbles? 98. And fourth pick is what? Okay? Is that okay so far? We A-okay? All right. So if I pick 4 marbles without replacement, what is the probability they are all red? So what's the first choice if they're all red? How many red marbles are original? 25. If I picked a red marble out and I didn't put it back, how many red marbles are left? 24. If I picked 2 marbles out and they were both red, how many reds are still left? 23. And if I picked 3 marbles out and they were all red, how many red marbles are left? 22. And this is where you definitely want to use a calculator, because when you sit there and stare at these numbers, there's no way that you can multiply them in your head that quickly. If you can, you have a gift that you should keep. So that comes out to, our numerator is 303,600. And then bottom,
I see.
940. And I can reduce that 600 divided by, and I would never want you to reduce something like this by hand. One of these days I'll show you the trick that the calculator does, which is pretty amazing. Calculator won't do it. It's too big. Holy cow. So I have 303,600 ways out of 94,109,400.
Oh my lord.
Which as a decimal, might be easier to look at as a decimal, 0.003. So this will happen 3.3% of the time.
Just be on a test that much, that big one.
If you have a calculation, worry about it. Right? I'll bring my other set in too, so you have the bigger ones. 0.3% of the time. Hey, let me ask you all this. Is it more likely that this would not happen? Make sense? Okay? And again, this is the foundation of how games work. Start dealing with probabilities. So you're taking a shot at a chance. Okay? If they had a show on TV, or let's say they had some sort of lottery, or let's say, you ever see, let's see, during college football now that you had some of these championship games, for the divisions, they have the Dr. Pepper where they throw the football into the thing, right? But then at some basketball games, even college games, they will do something during halftime called the halftime shot, right? And if the person makes a halftime shot, they win. Okay, and it could be a certain amount of money. So now sometimes they'll say, give us $1 to do this shot. If you hit it, then you can win this prize. Sometimes they'll say, you don't have to donate money. You can just go out and take the shot and do it. So is a half-court shot a hard shot to make in basketball? Yeah, there's a reason why the guys get as close as possible to get a 2-point basket. There's a reason why the 3-point line in basketball is a little bit further away from the inside key, right? But the half-court shot is really tough. You all right? Head on down. So the half-court shot is a tough one. So a lot of times there will be an insurance rider. So a company could actually go. So like, let's say the Denver Nuggets had a basketball game, and they want to have a half-court competition. And they're going to say, we're going to pull 5 people out of the audience. Somehow they've devised some way of saying, if you're in this seat, or whatever seat, we're going to pull 5 people out of the audience and have you do a half-court shot. This insurance company will write an insurance backing, and the insurance company is betting that nobody will make it. Okay? The Nuggets are betting somebody will make it. So let's say there is a $25,000 prize for making a half-court shot. You're going to try pretty hard to make that shot if you're chosen, don't you think? If they're like, hey, you get a free stick of gum if you make it, you're just like, yeah, boom. Who cares, right? But you put a monetary value on it that's like, dude, that's going to change things. Okay? I'm going to go on a trip if I win. So that insurance company will say, okay, we will hand, if you choose 5 people from the audience, and it doesn't matter if they know the game of basketball or not, you're just going to choose 5 people from the audience. They're going to come down, they present their ticket saying, yep, that's the ticket we were looking for. Take a shot. You get 1 shot. Okay? That insurance company might say, it's going to cost the Nuggets $5,000 for us to do this. So the Nuggets write a check for $5,000 to that company. That company, if that shot is made, no matter if all 5 are made or just 1 of them are made, will pay out each time. Because the insurance company is betting that everyone will miss. And they're like, sweet, we get to keep our money. So that's kind of a routine. You know, is this the probability of making a half-court shot? I have no idea. We would have to run some other data in order to do it. All right, finally move on to the next problem. Come on, baby. All right, let's see if we can make our pen work again. Yes. All right, problem number 3. You roll a die twice. Now remember, die means you're rolling a singleton. So you have 1, 2, 3, 4, 5, 6 on a traditional die. Agreed? What is the probability of rolling 2 5s? Okay. What's the probability to roll 1 5? How many outcomes are there on a die? How many sides are on a die? 6. There are 6 outcomes. What's the probability I roll 1 5? There's 1 6. If I probability to roll a 5 and a 5 on 2 separate rolls, I have 1 out of 6 times 1 out of 6, so 1 out of 36 if I multiply it. What is the probability of rolling at least 1 5? This is where we need to look at the complement again. Okay? So at least 1 5. Okay? So that means I can roll a 5 and a 5, or I can roll a 5 and another number, or another number and a 5. Agree? So what is the probability of a 5? It's 1 out of 6. What is the complement? So the probability of not 5 is 5 out of 6. Do you agree with that? So let's find the probability of not rolling a 5 and not rolling a 5, and then we do the complement of that. So I'm going to go probability of not 5 and not 5. So that's 5 out of 6 times 5 out of 6, which is 25 out of 36. So there are 25 outcomes out of 36 outcomes that won't allow you to have a 5 in one of your rolls. So I'm going to find the complement of that. So I'm going to go 1 minus that. So that means this changes to 36 over 36. If you subtract those, you're going to get 9 out of 36. You could reduce that. 3 goes into both. It's 3 over 12. Actually, I can reduce that to more. You have a 1 in 4 chance. The probability is 1 out of 4 times that if you were to take that die and roll it once, get it back, roll it again, that at least one of those numbers would be a 5. And what is the probability of observing exactly 1 5? I roll the die, pick it up, roll the die again. I want only 1 5 to be rolled. Okay? So first roll of the dice is 1 out of 5. Now, oh, excuse me, 1 out of 6. Sorry about that. Okay? Now it doesn't matter if I put the 1 out of 6 first or second. Now, what's the probability on the second die if I roll it that we don't get a 5? What's the probability if I roll the die at any time? 5 out of 6. Okay, so it doesn't matter if I had 5 out of 6 as the first roll or 1 out of 6 as the first roll. It doesn't matter. So if I multiply these together, because I multiply, it doesn't matter order. 1 times 5 is 5. 6 times 6 is 36. So you have a 5 in 35 chance that you see a singleton 5 happen. Wow. All right. Let's do some quick notes. Yeah, it's quick. 5. Sorry. 3. Sam, you got one there. All right, statistics, day 2, probability, bivariate, and contingency tables. We should be able to kind of, whatever we don't hit, we'll cover. Okay, so I'm on slide 2. Okay, so go ahead and copy these down. Oh, there? Oh, you guys are set then. All right, good. Save time. So categorical data is information that is categorical and descriptive measured. If I wanted to say, you know, how many people in here are wearing black shoes? There's the category. Black shoes is our category. Okay? Bivariate, or bivariate, however you want to say it. Data is in 2 variables, subject, used to analyze relationships. How many boys in here are wearing black shoes? Okay, we've set a category of boys, black shoes. Contingency table displays the frequency of 2 variables. So how often something happens. And conditional probability, the probability that one event will take place given another event has already taken place. Okay, so going to our next page. This is pretty quick. Ready? We have 100 people up there that are dealing with stuff. Some are right-handed, some are left-handed, some are male, some are females. Agreed? Watch how fast this is. What is the probability that a randomly selected student is a male? How many males are we talking about? 52. So 52 out of 100. What is the probability a randomly selected student is right-handed? How many right-handed students are there? 87. So 87 out of 100. Does that make sense? What is the probability a randomly selected student is left-handed and female? So left-handed, there's 13. How many females are left-handed? 4. So what is the probability that they are both? That's 4 out of 100. What is the probability a randomly is female and right-handed? Female right-handed is 44. So 44 out of 100. And then what is the probability we selected male? We randomly selected a male, and if being we've already selected them, and they are right-handed. Okay, so then how many males are we talking about in this whole study? 52 males. Okay, so my denominator here for E is going to be 52. How many are right-handed? 43. So there's a condition that went with this. What is the probability a randomly selected right-handed student was a male? What is the probability a randomly selected male is right-handed? What is the probability a randomly selected right-handed person? So how many right-handed people are there? There's 87. Okay, and how many of those are male? 43. Sweet. All right, so I will make sure to bring that back. I will cover the rest of it. I want you to start this. Notice I'm not collecting stuff. Doesn't mean don't do it. It means I want you to be able to keep it at you because I want you to use it as your notes a little bit. But I want you to get a good start on this, okay? 4, 5, 1, 2, 3, 4.